That would be cool. So last time we did first order difference equations where we had y2 equals wt plus v1 wt minus 1 plus v1 squared wt minus 2 plus v1 cubed wt minus 3 plus dot 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 kept on going. Correct. Yeah. And W sub t here are noise of some sort. As I mentioned, your book starts by saying, okay, we'll just treat them as scalars, but in practice, those are all quantum variables. And I gave that example. So what if you are today as a person? It's just a linear combination of random things that happened in your life in the past multiplied by those values, right? Now this simply says, you know, only one order. In other words, one difference. So all the way up to there will be significant. Everything past that will not be significant. But going back to my philosophical logic example, that's not reasonable because we may not regress just on, you know, past one day, but maybe at least 20 days, right? So, and some people obsess over the past significantly. For them, it will be 365 or 800. Yes?
As a relief for anxiety.
Right. So, first order difference will go theoretically all the way up to that point. And also, phi1 would converge under a condition. So I can rewrite this as 1 over 1 minus phi1 multiplied by wt. That's what we did last time. Yes? And then from here, I want to write it as a sum, which would be quite obvious. I equals 0 to infinity, phi1 raised I multiplied by wt. So when I plug in 0, I would end up getting 1. 1 times wt is wt. When I is 1, phi1 times wt. Oh, forgot the I, very important. Phi1 raised 1 is phi1, and I is 1, I get 1. When I is 2, phi1 squared, I is 2, wt minus 2, and so forth. Wt minus I is, of course, a constant. Oh, it's not a constant. We'll keep it as is. But just this part right here, it is an infinite sum of a geometric series. I take that back. Those i's come from the lag operator, so it is simply wt. Remember, we had phi1 multiplied by L, which is the lag operator. So the lag as we apply will result in t minus I and so forth. And that would simply be a geometric series, and we would require phi1L raised I as some constant A. The thing about geometric series is that we want phi1L to be bounded by 1. In other words, if it exceeds 1, the series will not be convergent. What do we mean by convergent? As you go over and over, go on and on and on and on, all the way up to infinity, things have to become 0. Do you agree? Yeah. So if at 256, you are still at a very high value for phi or phi raised to 256, then you're regressing way too much. So we agree. So it has to decrease. And the only way that would happen is if this condition is satisfied. Good so far. Now, keep in mind, L is an operator. And operators, it's kind of silly to say an operator must satisfy a condition. So what we do is we rather use a variable to come up with a solution. So going back to that expression, we will rewrite that L as some letter. Your book uses Z. That is typical. So going to multiply by 1 minus V1L on both sides. So I end up getting 1 minus V1L times W of YT is equal to WT. So we're going to replace that L by, say, Z.
Is that mostly just a thing?
It's more of a theoretical thing. In the sense, you can't say, I have an operator, and I'm going to come up with a condition for that operator. In other words, think of it this way, integral sign, right? Integral is an operator. So this is an operator that acts on, say, f of x dx. I can't say, oh, that integral has to converge to 0. That doesn't make any sense. Likewise, if I have derivative of f of x, this simply means d over dx is an operator. You can't say the operator which has to satisfy a condition, right? But if I arbitrarily make that a variable, say z, then I can impose a condition on z. Does that make sense? Now, this is what we call a characteristic polynomial. And combining chapter 1 and chapter 2 together, because the book is going in different directions. So you have a lot of reading to do, but if we do it this way, it'll be nice and you can just stick to the notes and understand the basics better. So what we want is that this must equal to 0. So it will become 0 if that is 0. Do we agree? So we'll set 1 minus v1, z is equal to 0. One is equal to phi1 times z. And that would give us a solution, and that solution z is simply 1 over phi1. There's something you've got to note here. Our condition for phi1 the absolute value has to be less than, absolute value of phi1 has to be less than 1, and phi1 cannot equal 0. Let's see if that makes sense. Well, theoretical standpoint, if phi1 is 0, then I'll have divide by 0 here, right? Can't be 0. And from a practical standpoint, what is our understanding? If phi1 is 0, that's gone, that's gone, that's gone, everything is gone. And we end up saying, whatever you are today is just noise, you mean nothing.
And we call people babies.
Right? It's completely random. If this is noise, then you're noise too. I'm telling you, there is no meaning to you, you're just noisy.
So in other words,
Does that make sense?
It really is babies, because babies just scream all the time.
Well, look, if you think about it, but then a newly born baby is definitely noise,
Yes.
right? That's a good observation, Alex. If it's a newly born baby, today is going to be based on today, it's just noise. Has no experience at all. But over the years, it's going to gain experience. So phi1 cannot be 0. So when you become an adult, you can't say, oh, phi1 is 0, which means every waking day, you're just random noise. No, I don't want to hear about it. So phi1 is not equal to 0, phi1 is bounded by 1, and that would simply imply here the absolute value of z. Let's say, if you remember your algebra, if phi1 is bounded by 1, in a sense, phi1 is always a decimal value between 0 and 1. And what is the condition for the absolute value of z? Greater than 1? It has to be greater than 1. Later on, when we get to chapter 3 and we start discussing autoregressive models and moving average models, we will see that if I'm looking at the characteristic polynomial, the condition that we impose is this. So we will simply say we have introduced the concept of the unit circle in complex plane. We want everything to be outside the unit circle. But if I'm looking at things on the left-hand side, we want everything to be inside the unit circle. And then there is the concept of the unit root, which simply means you lie exactly on the unit circle. There are some consequences for each of those conditions, and we will get into detail as we go along.
Can you repeat those or you'll just repeat them if needed later?
So these conditions are important for the processes that we'll talk about later. But the key difference is if you are looking at the characteristic polynomial from the perspective of the characteristic polynomial, we want the value of z, the root of z, to lie outside the unit circle, greater than 1. But if we are looking at it on this side, we want the coefficient phi1 to lie inside the unit circle. In other words, it has to be decimal values. And there are cases where the roots will end up lying exactly at 1. And those are called unit roots, and I think we cover that later on. So the concluding remark here is it matters as to what you're looking at. So are you looking at from the perspective of the characteristic polynomial, or are you looking at from this side using that? Good. Okay. Okay. I'll do a simple example. Can I erase this?
What kind of cats do you have, by the way?
Oh,
While you're racing, what kind of cats do you have?
you've seen them in my virtual
Yeah, that's true.
meetings. last semester, right?
Yeah, but I think I always see one.
They did see there. Berkeley's remarks see there. The one you see, the one you have seen during our appointments, is the oldest one, and he is the most social one. The other one is social also, but he just doesn't like my meetings.
You should bring him to class one day.
No, it's against college policy.
Be all pretty already all dressed up. Leave the two. Let's call your favorite cat. You end up feeding your cat at 2 in the morning, and you just say, go away.
Oh, I shut the door and made him go away.
Is that Wi-Fi or
Yeah, no. That's how you like it. I'm right, you this way.
Well, I do that too, but maybe it's just a variable, and maybe you write it down.
I see. It's a 9.
I mean, granted, I write my 4s are gonna be different from almost everyone else, so. I understand.
Good. So I just specify it as noise, but I'm not calling it to the white noise. In other words, I'm not saying it's normally distributed. And let's see what happens. First, we've got to realize that phi1 is within 0 and 1. So things should work nicely. So
But it means equal to what one,
it's the same thing, right? If I say that to be the condition, that holds true also. You mean you want me to put equal to?
I mean, then it makes it true.
Yeah. I see what you say. I thought you meant to say phi 1 is just equal to 3. So that satisfies the condition, so we can go, well,
Well, isn't P1 just equal to 0.1, because that's what you wrote.
come again.
Isn't P1 just equal to 0.1, because that's what you wrote.
So I'm just writing it as a condition,
Oh,
right? What is our condition? We require the condition to be the absolute value of, phi 1 to be less than or equal, less than 1. So if I wrote it that way, the condition absolute value of phi 1 less than 1 is satisfied.
yes.
So we'll start with y sub 9. Y sub 9 simply means W9 plus phi 1 WT 9 minus 1, 8. Phi 2 W 9 minus 2, 7, excuse me, phi 1 squared. Phi 1 cubed W 6. Phi 1 raised 4, W 5. Phi 1 raised 5, W 6. Phi 1 raised 6, W 5, 4, 3, 7, W 2. Phi 1 raised 8, W 1. Phi 1 raised 9, W 0. Looks painful. On an exam, we won't go this far. I'll ask you to truncate somewhere. I'm just trying to make a point. Now, let's see, what is an easier way to evaluate this?
Maybe add the like terms.
Huh?
Maybe like add the like terms together.
Add the like term. Okay, calculator is your friend, right? So we're going to use the calculator. So what we have here is W9, phi 1, W8, phi 1 squared, W 7, and so forth. So all the time points are fed to list 1. W is 1 over t plus 10. Since the time values are in list 1, I can simply write list 2 as 1 divided by list 1 plus 10.
Are you, do the 1 divided by list 1 again?
Go up and simply start typing. 1 divided by. Look up. Did you go up to L2?
Yeah.
So 1 divided by second 1, list 1 plus 10.
Okay.
Good. We just have to figure out. We will define phi 1. What is phi 1?
0.1.
0.1. List 4 is simply okay. I'm entering all the free values here, top 0.1, and you can see the power has increased from 0, 1, 2, 3, 4, all the way up to 5, 9. So I'm going to change list 4, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Good, with me so far. You see where I'm going with this. So what I'm simply doing is I'm taking the time points for W. I'm putting all the time points in list 1. And I took the expression for W and I put it in list 2. And list 3, I'm having all V1 values to be 0.1. List 4, I'm putting the powers of V1. Now, all I have to do is define list 5 as list 4 raised, or 0.1 raised to the power of L4. Right.
So you can just do L3 raised to the power of L4.
Yeah. And now that I think about it, we didn't even need L3. I could have simply did, 0.1 raised to the power of L4. It's okay. So L3 raised to the power of L4. Good. Enter. Those are all the values that I have. Did we get this? Now, what should we do? We have to multiply the powers of V1 with W's that we evaluated. The evaluated W's are in list 2. The evaluated V's are in list 5. So list 6 is simply list 2
9 with 5.
times list 5. With me, enter. That's what I get. Good. Wait, I can get all 6 here. List 2 times list 5. List 2 has all the W values. List 5 has all the V1 raised K values. I multiply them, I get L6. Now, how do we find the final answer? We just have to sum them together. So I could simply do start over to calc 1 last pass, list 6, because that's going to give us some. So that sum happens to be 0.0588. Good.
Are you switching to R now?
Not yet. Because this is useful for the homework.
No, I get that. I don't remember what.
So for the next time, Y10,
Can you pull it back up on? So I should have written this down, but like.
you should have.
if we were doing the calculator, just take to write it down, which is my favorite.
So we're starting at time 10, so 10, 9, 8, 7, 6. 6, 5, 4, 3, 2, 0, 1, 0. We have to stop at 0. Does that make sense?
Yeah.
We can't go past 0. We don't have to change this because that expression does not change. That doesn't change.
Well, you need an extra 0.1.
Oh, you are correct. That should be 1.
But you need to rerun the.
Looks like it. I thought it would do it automatically, but it did. So L2 is the expression for WT. So 1 divided by list 1 plus 10.
Then L3, you need another.
So L3, we need another point. Okay, 0.1. L4, we need another, so which is 10. And we have to run this again.
L5 was.
L3 raise L4. And L6 is simply L2 multiplied by L5. In other words, we are multiplying all the phi values with the W values. And those are the values that we have. Now we need to find the sum of list 6. And we end up getting 0.055. It went down, but only by a tiny bit. Do we agree?
And you want us to do the same thing for Y11 or?
Yeah, go ahead and let's do it for Y11 also.
By the way, so you don't need to reinsert it to everything. My mommy says so too.
I know, we know what it is. Jet. So we are going to do the same process, but only this time, since it is Y11, we are going to start at W11 and go all the way up to 0. Instead of changing each one of them, I'm just going to go to the very end and put 11. Right. Doesn't make a difference.
Make a huge difference.
Huh?
It just fundamentally bothers me, but that's.
So it wouldn't affect.
Wait, it just lost 0.
Oh, it took out 0. I see what you're saying. It's just gonna mess everything up. It's fine. Won't be lazy. 11, 10. This is why programming language is not effective.
Flat 4.
I don't write. Okay. So L2 is simply the expression that we have for W. So that would equal 1 divided by the time point second L1 plus 10. Enter. Everything gets computed. Okay. So we need to add 0.1 one more time. So 0.1. And here, that 0.1 would correspond to phi1 raised 11, right? Because we're just going to keep on going. So 11. And that is L3 raised L4. Enter. Lastly, it is simply L2, which contains all the W values that we evaluated, and we are going to multiply with the phi powers that we evaluated, which is the net 5. Enter. Now we just have to compute the sum of list 6. There is just a sum function, you're welcome to use that, but this is what we have. We get 0.053. I have defined W sub t to be 1 over t plus 10, right? In practice, this is not the case. This is a deterministic mathematical expression. In practice, we would have W t to be noise values, correct? So what we're going to have is noise that is normally distributed. And if we use that and fit the model, we're going to get a phi1 value. And that phi1 value is what's going to determine how the forecast is going to be. Does that make sense? So this would form the underlying principle when we get to an AR1 model. Are we clear? So if you understand the difference equation part, you will easily understand the AR1 model part. Good.
What is an AR1?
Nations, chapter 3, we'll get to that. So, are we clear?
Yeah.
Yes. Now, we're going to extend this to a second order difference equation, and second order difference equation would directly relate to an AR2. Does that make sense? So, can I erase this? The key items to note: the condition for phi1, the characteristic polynomial, and how the values decrease as we go farther and farther. So when I get to AR1 model, it will make practical sense as to why things behave the way they do. Good. Second order difference equations. Let's see if you can tell me what this would look like. So we know yt equals phi1 yt minus 1 plus wt. Wt is the noise component, and that's what we did earlier, and that is a first order difference equation. I want you to guess what the expression would be for a second order difference equation.
Would it be yt equals v1, yt minus 2? What's the v2 minus 2?
Yt equals,
Would be v1 or v2?
you tell me,
v2.
phi2,
Yt minus 2
yt minus 2,
plus wt minus 2.
wt
T minus 1.
I'm just having T. Your case is like tea, coffee. It's better. T. Okay. Do we agree with this or do we disagree with this?
I mean, I can see how it could be WT minus 1.
Okay. You're getting close. Well, why would that be?
Well, because I mean, like, if you're subtracting by 1 for the other t's, then you might as well do it for that one too.
Right, so in that case, this would be t minus 1, t minus 1. Right?
So probably just leave it then.
Okay, I want you to look at this from a very practical sense. So, second order would mean whatever we do at time t is related to t minus 1, t minus 2. Yes? So, whatever I said here, does that get anywhere closer to this? Do you want me to repeat that? So time t is dependent on t minus 1, t minus 2. Whatever I said, mentioned here, does it agree with that equation?
No.
Why not, Alex? You're the one who gave me this.
Well, I'm also the one who's guessed as well.
Okay, why did you say no?
Because you're missing the t minus 1.
Exactly. So when I write it this way, so I'm at this point, and I'm just jumping over there. So still, it's a one-step jump. It's a one-step time difference. That time point is dependent on this time point. This is also a first-order difference equation, right? So this is not correct. A second order difference equation would be yt is equal to phi1 yt minus 1 plus phi2 yt minus 2 plus wt.
Oh, I got half of it.
Excuse me?
So I got like half of it.
Yeah. And WSRT is our usual noise component. Now what we're going to do is we're going to rewrite this in terms of the lab operator. Yt is phi1 L yt. L times yt would mean it applies to lag one step to yt. Phi2 L squared y17. Two lags applied to t, which would make it t minus 2. No lag there, so it would just be wt. The other method to do this is recursive substitution. But imagine it was quite painful for us to do it for one step. Now we have 2 steps, so you have to go back and substitute 2 of them, simplify, substitute 2 of them, simplify, and it's going to take forever. And if we have to generalize it for a repeat order difference equation. So the effective approach is to use lag operators. So if I move it to the other side, I have yt move those two to the other side, yt minus p1l, yt minus p2l squared, yt equals w sub t. Do we agree? Yes. And that would be 1 minus p1l minus p2l squared multiplied by yt equals wt. What is the characteristic polynomial? What did we do to get the characteristic polynomial? So it's certainly to perform these operations on an operator. So I'm going to replace it and write it as 1 minus p1 z minus p2 z squared. Good. And we will see this later on. I don't know what your book uses for the notation of this characteristic polynomial, but in practice, uppercase p as a function of z is the notation for the characteristic polynomial. In the previous case, uppercase p of z was simply 1 minus p1 z. Does that make sense? So keep this notation, because when we switch over to moving average, I will use the notation uppercase theta. Does that make sense? Some people use psi or average with that psi or something else. So how did we express yt in terms of wt? Well, we divided by 1 minus v1l, wrote it out the geometric series, and then things worked out fine. But if I take this and divide it, I can't divide the wt by that term, I'm not going to get a geometric series. So how do we get to an expression for y in terms of w if we have a second order difference equation? And clearly, this is a quadratic function in z, right? Or quadratic equation in z. So we pick quadratic formula, we might get somewhere. Does that make sense? So good stop for introduction to second order difference equations.